have it about 12:40, so I will start with the preamble and then people can kind of wander in as we're doing that. I'm aware that although English is my first language, I can talk a little quickly. So if you're struggling with the speed I'm speaking at, just wave your conference pass in the air and I'll know to slow down. Okay? So the topic of today's talk is remote procedure calls, RPC. And what I want to do is dissuade you from using them. And I want to kind of suggest what the actual better alternative to remote procedure calls is, which is messaging. I'm going to tell you the answer at the beginning. But we'll explain why actually a lot of what people were building in RPC is valuable. It's just this last mile of RPC that's a problem. Part of the reason I do this talk nowadays is because I think we felt that we'd won the war against RPC and no one was using RPC anymore. But of late, as people have begun to build microservice architectures, people have begun to use RPC frameworks again, things like Thrift, which is Facebook's RPC framework. And so I think it's quite relevant to bring up again why you probably don't want to take that approach if you're building a microservices framework to use RPC as the inter-process communication mechanism. Who am I? Most of that is dull and boring. It just says that I'm old enough to have grey in my beard. And it also says that the point at the bottom is the one that I care about most of all, and that's that just because people stand up on the stage and talk to you doesn't mean they're any smarter than you are. It just means they're maybe a bit more confident. And if I can understand it, I'm absolutely certain you can. I'm not particularly super smart. That's where I work, Huddle. We're an internet startup based in London. We do places for online collaboration, usually at the boundary of an enterprise, so a kind of extranet model. You don't really care about that, apart from the fact that I don't work for a consultancy, I have nothing to sell you, I'm just giving you my experience of these ideas. And the crazy titles won't really help you, but we'll talk essentially about RPC. We'll delve into its history, and we'll explain how it works. And then we'll show an example of actually using RPC, and then we'll basically run through what the problems are with RPC, what the difficulties are you'll face, and then we'll explain what a better alternative is to RPC. Okay. So what do we mean by RPC? What is that phrase? So this is Wikipedia's definition of a remote procedure call. And it's fairly straightforward. Essentially we're saying I have two processes and I want to communicate between those two processes. Okay. So I want to do inter-process communication. And RPC suggests that the paradigm to use when talking between one service and the other is the same as the procedure call. So when I have a local procedure call, what I just call a function, that paradigm should be the same when I'm calling this other process. And in the epitome of RPC, from the point of view of the developer, it should be seamless. I'm just calling a function, and maybe it executes here, maybe it executes here. Okay? So RPC is a way of us saying we want to do inter-process communication, and our preferred approach is to make a procedure call, but have that procedure call execute on the other process. We may say, well, I don't do procedures. I do object-oriented programming now, Ian. This is not the 1970s. So the object-oriented version is called remote method invocation, and it is essentially the same thing. You just basically invoke a method on an object. The paradigm is the same. I want the call here to look like a local call, but I'm actually calling an object which is over here. Okay. And that is essentially what RPC is. But we'll delve into a bit more detail. So those of you that get excited by reading white papers, there's a white paper called RFC 707, written by a guy called James White. in 1976. And he looked at this idea of saying, how do we do inter-process communication? How do I get this process running here, talk to this process running here, often on separate machines? So these are the days of the kind of Unix time-sharing networks. And he looked at what the existing ways of doing that were. And he looked at things like FTP, SMTP, all these kind of paradigms that existed where you essentially from your process, say for example a telnet session, would call onto the server and say for example I want to do FTP, I want to upload a file. And he said, that's kind of our main paradigm today for doing inter-process communication, or it was in 1976. But that's very inefficient as a way of doing future software development. And he looked at all of these protocols and he said, there's something very interesting about them. Essentially, if you look at FTP or remote job execution, what they all do is they issue a command, for example, upload file, and they get a response back from the server, say a status code saying, yes, your file has been uploaded, or no, your file didn't upload successfully, and some kind of message, like an error message if it fails. And he said, they all have this same paradigm, but they just have different names for the different commands they use. And he said, what we've not really ever done is picked up on this fact that there's an actual underlying consistent approach to how we do inter-process communication. And so he said, essentially, you can take both remote job execution and FTP, and you can say everything is just a variation of this. I issue a command, a space, a set of parameters to that command, so upload in FTP, a space, a parameter, the file I want to upload, character return line feed, and then I'll get a response back from the other process saying, you succeeded or failed. Okay. And he said, actually what we want to do is take this paradigm and try and use that to process communication. So he said, what if instead of having to deal with individual protocols like FTP, SMTP, RJE, we actually went away and said, I'm just going to build a library that lets a client process send a command to a server process and get a response. Then I'd only really need one library, and I could write that library for every programming language I needed to use. I could write basically this client-side library and the server-side library. I could just send commands. Yes, we have to agree for every application what the commands are that are valid, but I'm not having to basically write an entirely bespoke framework every time I want to basically communicate between two processes. In 1976, this was very exciting, by the way. So he created this thing called the Command Response Protocol. Okay. And it had a number of ideas that basically he said should happen. So it should permit invocation of named commands by the remote process. So what it enables me to do is say, you have a list of commands. What I'm going to do from my side is just say, okay, I want to invoke this command, which you understand, and here are some parameters for it. Okay. And permit command outcomes to be reported in a way that adds both the program and the user. So what he means by that is it should send me back a code to tell me whether it succeeded or failed. And if it should send back some text, I can display to a human being, so the human being can understand what happened as well. So you see that today even for HTTP, right? HTTP returns HTTP 200 OK. And you're actually, HTTP, you're issuing a command like post, get, etc. effectively to the service. So it's still following the same idea. I'll allow an arbitrary number of parameters arguments to a single command. So essentially we can send a lot of arguments. Again, in theory, things like HTTP respond to this, right? With entity bodies or query strings. Representations for a variety of parameter types, not limited to character strings. So in other words, we have to have some mechanism for agreeing what the types are we're going to send over the wire, and we have to do more than just strings. We may need to send numbers and those other kind of values. So whatever, we can build some kind of runtime that understands that. So it could be XML or JSON nowadays, but it could be things like protocol buffers, that kind of thing. Permit commands to return parameters results, that's fair enough. And these three are a bit more complicated. We'll dive into them in a bit more detail later, but one is to say, actually, rather than just simply saying my client calls my server, We want to move away from this idea of having clients and servers and just have processes that can call each other. That's a truly distributed system, right? Nobody is essentially the controller of this process. There are just things talking to each other. And a process should be able to work concurrently, right? It should be able to say, actually, I can service more than one command. And effectively, you should be able to suppress responses from the sender if I say, it's just fire and forget. I don't need the answer. And so he said, actually, this command response idea that he parsed out of those existing application protocols, you can kind of rewrite it like this. So I'm going to send you a message. Message is going to have a type, so in this case, command, or potentially response for the return value. I'm going to have a command name. What command do I want you to execute that you say you implement? And what arguments am I going to provide to that command? And again, a response to the outcome result. So you can see things like, HTTP work this way, right? HTTP says I can send you a get or a post or a put. I can give you some arguments. They're all generic ideas or versions of this idea. I also have an ID here, and the idea is that I can correlate between the message I sent and the response that I receive. And so the thing is, if you talk about command and response, a lot of the time what we're implying is that we have a user sitting at the one application process who's requesting for something to happen, and that's being sent to another process. So actually we could call these things request and reply. And actually by changing that name, it implies more that two processes are simply communicating with each other about the state of something, right? So this is where request and reply comes from, back in 1976. And we can say, I want to request basically something, here's the operation code, that's the identity of the command I want you to use, here are some arguments, and then you can give me a reply which tells me whether it succeeded or failed. If it failed, gives me some kind of text saying, what went wrong. Okay? So we're all pretty familiar with that kind of approach today. Most inter-process communication you probably used is using some variation of this model that James White described in 1976. The way this becomes what we now identify as remote procedure calls, or at the time it was basically identified as PCP, which was a procedure call process, was he said, well, rather than simply arbitrarily giving you a request with an operation code, what I could actually say is that maps to a procedure and an argument. So the message I want to send to you is invoke this procedure with these parameters. And the response I get back is the return value from that procedure with the results. And he said, and the idea was that for a programmer, this would be straightforward because the framework would take away the understanding of how you marshaled this request. I'd simply call something like my method, my value 1, my value 2. And it would say, right, I'm going to take that and execute it on the server. And I will basically say to the server, call the procedure my method with the arguments my val 1 and my val 2. And then when that procedure had finished, it would return the result to me, and I'd see basically a return value from my procedure, right? So that's essentially this idea of effectively saying, making it look as though I'm doing a local procedure call. Right, so he called it procedure control protocol, but they're called RPC. Okay. That was in 1976. Nothing much happened with the idea until about 1984. In 1984, Xerox PARC, you guys know who Xerox PARC are, right? Xerox PARC are the guys that invent the GUI, the mouse, Smalltalk programming language. Essentially, modern computing as we understand it is pretty much developed in Xerox PARC. And the guys at Xerox PARC say, we're going to implement this idea. And they use a programming language called Cedar. Cedar is a descendant programming language called Mesa. I've never used it. Anyone ever used it at all and seen it? Okay. But it's one of these, research languages that no one else outside computer science ever used. And they said, we're going to build this. The key thing we want to pick up on, they said, is this idea that is this key idea for them that from the programmer, calling a remote process should be as easy as calling a local procedure call. And their reasoning is this. They said, for most software developers, if I want to expand the market for software developers, inter-process communication is hard. And many of them stumble on the idea of trying to basically call another process or use shared memory address space. And these ideas don't work very well, but they all understand how to write procedure calls. So if I can take away from them the burden of having to figure out how to do inter-process communication, and they can just make a local procedure call, we can widen the number of people that can do distributed systems programming, right? Because it's really easy now. I'm just calling a procedure, and it just happens that basically it runs in another process, but I don't have to see any of that, right, from their point of view. The runtime takes care of it all. And so some concepts that become important in RPC get developed at this point. So one of them is that the method programming language, a bit like, say, C++, has a separation between the interface definition and the implementation. So you know how C++ has a header file and the implementation file? Most of you familiar with that kind of idea? So they said, well, actually, if I've got this header file, that actually describes, say, the set of functions that are exposed from a package. And what I could do is, given that set of functions exposed from a package, I could generate from that a stub. And that stub's job would be on the client side to say, okay, when you make this call, what I have to do is package up the procedure name and all your parameters and pass that to a runtime, and that runtime will essentially then call the remote process, which will then have a corresponding auto-generated stub, which will take the command name and the parameters, essentially invoke that particular method for you, passing the parameters in, and then when the response comes, we just do the whole thing in reverse, right? We then package up the response, send it back. So I can auto-generate, was their idea, essentially these stubs that make it possible for the programmer to never have to see how this is working. And the idea is essentially the server exports this interface definition and the client consumes the interface definition. And so if you've ever done any programming with things like COM or Corba, you have IDL. Have anyone done any SOAP programming, basically web services? You have WSDL, so web service description language. That again is a language that describes the service doing the same thing. It's saying you can auto-generate a proxy or stub from this. So have everyone done WCF programming, for example? WCF, you auto-generate on your client basically a stub to call the remote service. Doing exactly this, it's taking WSDL, which essentially is interface definition language. It auto-generates the stub, which allows you to essentially make the call across the web service. And you just call something that locally looks like an object or a procedure. They also got into this idea, which is becoming bigger nowadays again, with microservices, service registration. So if I'm calling a local procedure, and my stub picks that up and gives it to the runtime has to find a server to give this basically call to. And the way that they did this was basically they said, well, we need to basically use some kind of registry where we will register people who provide an implementation of that service. So a service spins up and it says, I provide the following procedures, and it registers basically with something, and the client says, I need to find somebody who implements that, and I will then call them. So they used a distributed database called Grapevine. I think it exists today, but basically it's a key value store. And so when the server spins up, it says register basically in the key value store, and the consumer, when it basically needs to make a call, what happens is it uses an algorithm to determine which server to give the call to. Now what they used was closest. So they said, which is the closest server to me? But nowadays we use quite often a round robin approach. And this is essentially the predecessor of things like etcd, Zookeeper, Console, which do service discovery for you in a more modern environment. Okay. Anyone used Console or Zookeeper? Okay, a couple of hands. So essentially, things like Console are a key value store where essentially you can register services so that you can find them at runtime by discovery. Okay. Otherwise, I want to show you an example of actually doing that. You have to hard code in the location of your service. You have to say, you can go and find my remote procedure service at HTTP localhost 9000, and that means if I ever want to change where that lives, that becomes difficult, right? So this is the early version of that. So this is what happens. Right, we'll run through it. Caller and the callee. So I start here, I make what looks like a local call. I call foo with myval1 and myval2. My stub, which has been generated for me, so they had a thing called Lupine that did this for them, but say WSDL in WCF does that for you. And I'll pack up the arguments. So I'll say, okay, I've got these two arguments, myval1 and myval2, and I've got this method name to call, which is foo. I have some kind of runtime. The runtime says, I handle things like reliability, retries, network errors, that kind of thing, and I will make this call for you across the network to the other process. This gets the call, and it says I need to figure out what I need to do with that. So this is a method call to foo with the following argument. So it calls foo and passes my arguments across. Procedure runs remotely, then returns, and we say I've got a result back, a return value from foo, and it says I need to package that up, right? Give that to the runtime again, which basically handles transmitting over the wire. Send that back, I unpack the result and make it and give it back to you. So it looks like I've made a local procedure call. Make sense? We there? So that wasn't really the big uptake at that point, but the big uptake comes in the 90s. Anyone used any of these technologies? A few people, less than I'd have thought. So Corba and DCOM were the big object technologies back in the early 90s. Corba was mainly, very C++ focused, but outside the Microsoft stack. DCOM was the Microsoft stack equivalent. And then Java MI, .NET Remoting, anyone used either of those at the time? Yeah, a few people. And then we get into SOAP, so web services, right? They're just RPC in the most basic format. WSDL, as I said, is your IDL definition, and you auto-generate via Visual Studio your stub, so that you look as though you're making that call. Okay? Pyro is one for Python, and there are many other similar frameworks. So they became very big in the 90s, and that lasted into the early 2000s, and then we began to move away from them towards things like REST and AMQP, and we'll talk about why we did that later. Okay, let's change our pace a little bit. I want to give you a more specific example. So being English, I like a good cup of tea. So I want to talk about this classic problem we quite often give new developers of saying, well, if you want to understand how to break something down procedurally, how would you break down making a cup of tea? So here's a nice little flow chart for making a cup of tea. We get some water. We put the water into the kettle. We boil the kettle. We get a teacup, put a tea bag in, pour the boiling water onto the tea bag, and then we probably, and if you're in England, certainly, you're going to add milk and you're going to add sugar. And the interesting reason we talk about this quite often is it's a good example of something that can be broken down into a series of steps. And therefore, it's quite a nice way of looking at decomposition. So it's quite often used as a brilliant example. All right. So I've got some code here. Did it share my screen for me? Yeah, cool. Right, so let me look at the T server. Okay. So can you guys read that at the back? Is that, I can make it bigger quite easily. Bigger? Oops. Okay. This is Python code. I'm just using Python because it's really quite easy and it has low ceremony around it, so it's easy to read. So what we're doing here is we're using, Python has a XML RPC server. So we're going to use XML as the wire format to send an RPC message. And what I'm doing here is basically saying I'm going to create a server, so I can put some logging out. But I create a server, I create a local object called TDispenser, and then what I do is register a whole set of methods that essentially, whoops, the TDispenser implements. So I've got fill, boil, ready cut, pour water, add milk, add sugar, and done. So these are just procedures that I'm registering on the server to say export these procedures so that the client can call them. And Then I just start the server running. Okay. And you don't need to really understand the details of my T server. It doesn't really work particularly well. But essentially, there are a whole series of methods that relate to those processes that essentially perform the steps of boiling the water, putting the bag in the cup, letting the tea brew for a bit, and we can add milk and sugar to it. Okay? The main thing is they just give us some text back so we can actually see what's going on. All right. Just stop that. So I can start a T server like this, and you can see it just says I'm running. I'm ready to receive requests. And over here, you can see what I've done before is just start a T consumer. And the consumer just tells us as it calls each operation. I'll show you the consumer code in a second. Just like pause or we heat the water. And then in a second, we'll basically ready the cup, and then we'll let it brew. And after it's brewed, we'll basically add the rest of the stuff inside it. And that's kind of how RPC basically works. Now, if you look at the client, one important thing to understand is the T consumer So I have some stuff, I don't have any service discovery here, so that's why lack of service was a problem, because I'm hard coding a location. But the print statement is just so we can see the response, but if you look, I'm essentially making a procedure call, right? And I'm making it on this proxy, that's our stub that we talked about earlier. I'm just making the procedure call, but I'm making it locally here. So it looks as though I'm doing local procedure calls. And that's essentially RPC. What I can show you as well here is, just to make life a little interesting, is we can it's always a bit complicated to drive when your font is massive, but we'll so we'll just make it more verbose. And if you can, I don't know if you can read that or not, maybe too small for you, but up here you can see I'm calling a method called fill. Up here you can see I'm calling a method called ready cup, for example. So this is just XML that it's sending over the wire, and the XML tells it essentially that I'm expecting effectively you to call a method with a given name and there's some parameters. So you see when we get down to adding sugar, where's my adding sugar? Adding sugar, we actually have a parameter value to tell, say, how many sugars we're going to add. That's essentially how XML works, RPC works. It just means that the wire format telling me what method to call, what parameters to pass is all done in XML. Okay? And we'll come back to why that's important in a second. Okay. So I kind of said the talk is about why you shouldn't use RPC. So now I've kind of explained what RPC is and how it works. I want to explain why this is a bad idea. So the first problem is actually one that is called out in the original paper 707, and that's that we're lying. A local call works on the stack. It isn't going to fail. But a remote call goes over the network and has some kind of runtime involved. It could well fail. Now our runtime may try and make it as reliable as it can, but the reality is we may end up with, say, for example, a network error when we've made a local procedure call. So from the point of view of the programmer, what seemed very simple, I'm just making a local procedure call, has now opened me up to a whole range of unexpected errors which come from basically making a call over the network. And so it's deceptive, and we may not make the right choices. I don't really know whether or not, when I'm waiting for a response, whether my T server is actually there, making a cup of tea, or is errored in some way, right? When there's a pause, for example, when it's heating the water, what's going on? Is the server still there? Has it gone away? Am I going to get an error of some sort if the whole thing disappears on me? What happens if there's a problem? What happens if the server starts spinning for some reason, or the heater is broken? How am I going to get a response back necessarily? Right? This problem is often referred to as the fallacies of distributed computing. Has anyone seen these before? A few of you? Okay. So the fallacies of distributed computing say people commonly believe these things when they're doing inter-process communication, and they are not true. The first is that the network is reliable. In other words, when I make a call, it will succeed. You get transient errors all the time, particularly if you're not on a rack, but you're actually essentially talking on the cloud between two different shipping containers, right? The network is not reliable. Latency is zero. Latency is definitely not zero. Again, if you move away from a rack and you're in the cloud, you're going to find you start experiencing latency. The speed of light is a constant. You can't beat it. Bandwidth is infinite. Bandwidth is actually quite expensive. The network is secure. Well, we kind of all know that nowadays that's certainly not true anymore, right? We've all seen what the NSA will do to you if you believe that. Topology doesn't change. That means when I code in HTTP localhost 9000, I'm assuming there will always be a server at HTTP localhost 9000, or whatever the IP address of my server is. I'm assuming that will never change. But the reality is there may be in environments where boxes disappear and come up again and have new IP addresses. And so I have to be aware of the fact that I may not be able to rely on a fixed location for anything. One administrator is essentially a reference to the idea that somebody knows the entire, where all the bodies are buried, can make the whole thing work, rather than essentially there being lots of people and we'll get faults. Transport cost is zero, network is homogeneous, so less important to worry about right now, but they're all implications of we can't rely when we make a remote procedure call on success. And I've got another talk coming up at Safe at Any Speed tomorrow. I talk much more about these kind of problems and how you solve them. Blocking calls, essentially another issue here, right? RPC, by implication, blocks because it wants to appear as a local procedure call. Local procedure calls essentially block. So async RPC is kind of a strange idea because you're not really doing RPC anymore. But these things are going to block, and you basically chew up a resource waiting essentially for the response. Temporal coupling. So this idea is quite often described as temporal coupling. So temporal coupling is the notion that when I make a call, you need to be available to answer. Right? It's a bit like a telephone. I phone you up. If you're not there, I can't have a conversation with you. We can't deal with whatever it is you want to deal with. So RPC is like a telephone conversation, right? If you're not there, I have a problem. We can do a really simple demo of this. It's so trivial, it's almost insulting, so please don't be insulted. But essentially, if I start my consumer and there's no service, essentially I'm going to get a network error. No connection can be made because the target machine actively refused it, which I'm sure a few of you have seen, right? So my local procedure call has resulted in a network error, and the programmer needs to be aware that that's possible. Okay? But so this idea that I've made life easy doesn't really begin to hold water after a while, because I've actually potentially exposed you to considerable risk that you weren't aware of. So, if you live in the UK, like I do, you can fall out with your friends very easily by making their cup of tea wrong. And there's a big debate in the United Kingdom, and it goes like this. Should I put the bag in with the hot water and then, wait till it's brewed, take the bag out and then add milk? Or should I add the bag and the milk at the same time? I can tell you for free, people that add the bag and the milk at the same time are wrong and should not be your friends. But there are differences of opinion on how you make tea. Okay? One of the problems we have with a client sending these messages saying, boil the water, add it to the cup, now basically brew the tea, then add the milk, is that the client is always determining the best way to make tea for us. And in fact, the question we should ask ourselves is that the way we should really write our software? Shouldn't the tea server have all the expertise about making tea? Shouldn't it be the thing that says, I know the best way to make tea. Don't come to me with your milk and bag in at the same time nonsense. I'm the tea server. I will tell you how to make tea. But the problem, as you saw with the code we had, was that essentially the client knew an awful lot about the implementation of how we make tea. And in object-oriented programming, we have a name for this problem called feature envy in OO, where essentially quite often you basically set a whole lot of properties from your calling code, and essentially the business logic bleeds out into the caller from the object itself. Okay. And it's exactly the same problem on a larger scale, right? The client knows everything about behavior. All right, I might come to Ukraine and you might have an entirely different tradition about making tea. You might not put milk in your tea, you might put other things in your tea. Okay? So I might want my server to be able to make decisions based upon your locale, for example, and say, oh, well, I'm in Ukraine, I've been asked for a cup of tea, so I'm going to use an entirely different algorithm to make the tea at this point, because that's a different customer and different audience. And again, the problem is if the clients have that knowledge, then I've baked the problem in of trying to basically update my client rather than my server. My client should just say, I want a cup of tea, right? And the server should tell me what cup of tea is appropriate. I don't really have a demo of that. It's just more to remind you what the code looked like. We should say that the tea consumer code over here, as you can see, if I want to essentially put the bag in, I'm going to have to essentially begin swapping around the way I do procedure calls. And in an environment where you're distributing software, okay, that's problematic, because now I need to go and change all my clients in order to change my implementation. If I discover that I'm wrong and you put the milk in much earlier than I believed, I've got a lot of changes to make. This idea is referred to usually as behavioral coupling. Right? The behavior, the client understands the behavior that I am basically providing. And if I want to change that behavior in any way, what will happen is that I have to change the client as well as the server. And generally we don't want that. When I have two processes and I'm doing RPC and both those processes are on the same platform, .NET to .NET, Java to Java, things are fairly straightforward because, generally speaking, I can come up with a runtime that understands how to make that communication straightforward because we share ideas like type systems. But it turns out that in a lot of cases, the dream which people have with RPC, which is that I can write my client in one language, say for example .NET, write my server in another language like Java, begins to break down a bit. And part of the problem is that platforms don't necessarily have the same view about the information they're exchanging, the types that they're marshalling. So as an example, essentially if I say part of my tea machine asks you to load it with tea, right, I may be assuming that I'm going to get tea bags, but you might only have loose leaf tea and you're going to give that to me. Then I've got to make a decision, how am I going to deal with that? Do I wrap it in some kind of strainer and put it in my mug? Do I put it in my mug and then kind of strain the tea out? How am I going to cope with the fact that I expected a tea bag but you gave me tea leaves? And this problem plagued people in the 90s. So I used to do a lot of C++ programming, doing COM in the 90s. And the way that we worked was we realized that C++ wasn't the best language to write user interfaces in. So people would use tools like Visual Basic or Power Builder to write the interface, and then they call the C++ object, which would be running basically on a server somewhere instead. And strings were a nightmare, because C languages have zero terminated strings. where effectively you just keep reading the array until you basically get to the 0, and that's terminated a string for you. Visual Basic has a string where prior to the beginning of the string, there are 2 bytes that give you the length of the string. So you can't read a Visual Basic string in C and vice versa. So you have to marshal between one type and the other. And there are a whole set of string types, a bstro, wide string T, that were created to allow you to marshal this code. And when I was a programmer in those days, you used to write your method, and you'd spend the first 5 lines of code in your method just marshalling types back and forth between the 2 type systems. And it's painful. Okay? And one of the things that .NET was trying to solve was to say, oh, well, I should still have the same type system between components because it's so painful to do this. And this is referred to as the impedance mismatch. The other problem we tend to get with RPC is that we talked earlier about this notion of interface definition languages. We said, I'm going to basically expose an interface, and you're going to use that to generate stubs on the client to call the server. One of the problems with that is that when my generated stub is generated for a particular version of the server's exports. If the server updates itself by saying, I want to change this call, I want to change the parameters on it, you can usually get away with extension, adding new methods. The problem is that my clients, who may be stuck on an older version, are going to break when they call me. So usually to extend remote procedure control interfaces, what I have to do is actually say, I'm going to create a new interface with basically a new method on it to call to replace the old one. So old clients will continue to work, but new clients will be able to call the new method. So in this particular example, we obviously have an interface called ifoo, which has some kind of function in it, and in order to change the parameters, for example, what we have to do is, or add a new method, we have to create a new interface and add method there. And this versioning problem plagued people doing RPC back in the 90s. I used to deal with Microsoft interfaces that were things like, IOLA create factory 4. And used to have to query the server to determine which version of the interface it supported before we could do any work. Right? And this whole model that we originally had of saying, well, actually it's going to be really easy because it's just like a local procedure call, is beginning to break down at this point, right? I'm querying the server to see which versions of the procedure it actually supports so I can determine what to send it. I'm aware now that I may get a response back that actually indicates a network error, or I might get a timeout, rather than genuinely being effectively a response from the actual procedure. I might find that when my types get marshaled, I lose precision. So for example, I might send it across as a float and you change it into a double. Okay, think about JavaScript calling essentially over to another language and the lack of precision because its numeric type was really only a float. So this whole idea has begun to break down on us. But the question is, what should we be doing? If this doesn't really work, what does work? And the answer is really to use messaging. So interestingly enough, there was another RFC written about the same time called 684. And 684 is called a commentary on procedure calling as a network protocol. And it's a criticism, essentially, of RPC and PCP. And it says, RPC was pretty good up until a certain point. What it's saying is, this is true, right? This is true. You can actually think about the world existing as commands and responses. And this is true. We can actually make that generically request and reply for inter-process communication. The problem was when we went here and decided to make that our procedure name. If we'd stayed here and just said, I am going to send you a message, and that message essentially is going to has a payload with it, and you are going to respond to my message, then I'll be in a much better place. And the problem was only when I chose to make that procedure calls. And also the other stuff, right? The idea essentially of a runtime and service discovery and even marshalling of the arguments to help you, so that it's pretty straightforward for a program over here to say, I'm going to send you a message, and on the far side for the message to basically get received and sent to a handler for that message, it's pretty straightforward, okay? So you think about how, for example, you know, your average MVC server-side web framework works. You essentially write some kind of controller, and all that's doing is saying, I am receiving a message from HTTP. Your runtime has essentially marshaled the parameters into a call to my method, okay? And that's essentially what you want. And when you send from the far side, you're essentially saying, well, actually, I just want to make a call and have you deal with the issue in between. So you should prefer messaging overall. And you can, this applies both to either messaging middleware, so for example, AMQP protocol, things like RabbitMQ, Azure Service Bus, and it also applies to REST. REST as a paradigm is actually quite message-like, because you have a uniform interface, get, post, put, you're not actually calling procedures, and you're giving a payload. So that's actually basically forms the request-reply version of RPC, which is the good version. Okay. When we think about messaging, one way of thinking about messaging by contrast to RPC is this. RPC says, okay, fill the water, heat it, fill the kettle, boil the kettle, pour the water over the cup, put the bag in, right? Whereas messaging just says, make me a cup of tea. You know how to make tea, make me a cup of tea. So I give all of the concern about the implementation over to the server and just say, make me tea. And that's one of the reasons we prefer messaging, is because it immediately eliminates that behavioral coupling. We also, because we're explicitly sending a message, remove the problem that we have some kind of temporal coupling. We'll come back to REST on that, because we're tending to send it over middleware. So that means essentially we don't really care if you're up. We'll just put a message onto a message queue, and it will be answered and serviced at some point. Okay? And there are two types of message we care about. The first type of message is I say to you, make me a cup of tea. Right? That's okay, but it relies on you being available to make me a cup of tea. The other type of message, that's a command message. The other type is an event, and the event says, I could do with a cup of tea. Right? And I'm hoping that somebody will then get up and make me a cup of tea. That's the way that works. So I don't have in mind a specific collaborator. I don't know who's going to make me the tea. I just indicate my need for tea and hope something else in the network will service that request. And that's much lower coupling, because I don't need to be aware of a potential consumer of that message. I just need to know there are people out there and someone's going to be kind and make me a cup of tea. Whereas with this one, I have to be aware that there are other people out there who will make tea for me. Okay. And we can kind of like drop a diagram which says behavioral coupling, so there's a highest behavioral coupling over there and the lowest here, and temporal coupling, which is basically low up here and high down here. So high temporal and high behavioral is this, what we call a distributed n-tier system. So it's the classic model where essentially between layers we make calls over an RPC framework saying, I expect you to be up. I have no way of dealing with you not being up. I will block while basically you respond, chewing up basically the resource on my own side until essentially you return back to me, and then I'll deal with the response. I have high behavioral coupling because I'm probably the locus of control, as we call it, with the client. The client is essentially in charge of the operation, and it's giving you instructions about how to work rather than handing off to you. Better than that is to remove the temporal coupling by using messaging. So we say, I'm going to use some middleware, RabbitMQ, MSMQ, MQ series, whatever they call it now, Kafka. I'm going to use some middleware. I'm going to send you a message. What we're looking for is what's called guaranteed at least once delivery, which means once I put the message there, it will be available for a consumer at some point in the future. Once I put a sign out saying, please make me a cup of tea, at some point someone will come along, find that request and deal with it, right? I put my order in at the restaurant and essentially said, I want tea. They've taken it and handed it to the barista. He's going to make me tea at some point. Not necessarily now, but when he's available to do it. Okay. Down here is what we call emergency services. So this is REST, lives down here. So we have low behavioral coupling. We're basically using a uniform interface, get, post, put. We're sending a payload to you that doesn't say call a procedure, it just says update this resource or get me the resource. And you can map that to whatever handler, etc. you need internally. But it's called an emergency service because generally REST is temporarily coupled. Because you're actually saying to the server, here is my basically post, please respond to me. And so you're relying on the server being up. It's called emergency services because if you call them and you get a message saying, I'm sorry I'm not available right now, you're shit out of luck. Okay. And this model up here is event-oriented, which we just described. That's basically the best in sense that it's got low coupling and low behavioral, and low temporal, both temporally and behaviorally, right? I'm using middleware, so you don't have to be up when I send it. You can come and deal with the message when you want to. And I have low behavioral coupling because I don't know how you will respond. I just know that you know what I want. I say to you, I need a cup of, I'm thirsty, I could do with a cup of tea. You will respond by whatever means appropriate. Don't bring me coffee, obviously that would be a mistake, but, okay. So we're going to just summarize what we've talked about. So first of all, we talked about what RPC was. So RPC is two processes. They're inter-process communication. One is calling the other. And the paradigm that RPC wants to use is to say, this looks like a procedure call locally to you, whereas in fact it's executed on another process. And we said that this idea first came from an RFC 707 written by a guy called James White. And that his insight was that rather than having application-specific protocols, we could do inter-process communication by a library that had, say, runtimes and stubs, and was used to issue commands against another server, which he translated into basically procedure calls. So he came up with a command response protocol, and then later on, some guys at Xerox PARC went and built an implementation of this. And they built it on a language called Cedar, and they came up with some concepts that are important to us nowadays. Interface definition language, in other words, I define my exports so that you can generate a stub from that to do the call over the runtime, and this idea of service discovery via a distributed system key value store. And those ideas are still in use today. So I work on, if you're a .NET programmer, at Huddle we released an open source project called Brighter. And Brighter essentially does messaging for you, and it uses a dispatcher command model, so you do send, post, publish, that kind of thing. And we essentially handle that runtime and stub generation for you. So if you want to do that kind of messaging, you should go and look at that. We talked about distributed objects. We said how in the 90s, distributed objects became the big thing. People wanted essentially to have objects remotely. The other thing with objects, by the way, of procedures, you have to worry about lifetime. So you have to say, well, I'm creating an object. If it's got a state, how long will it live? Who kills it? Etc. And then we looked at the fallacies of distributed computing. We said the problem with all these ideas is saying, I want to make my remote procedure call like a local one. I want to make my object interaction like a local one. Is it defies the reality that networks are not reliable. And we said that we also didn't like procedure calls because they end up behaviorally coupling us. We know too much about the implementation of the server by calling this push button API. We want to make a single request and get the server to execute as it sees fit. And we said that they also suffer from this problem of the impedance mismatch. That the two type systems may not be the same, and the communication can get lossy, particularly around things like numeric types. And we pointed out the problem of versioning. If we're generating client proxies those client proxies are generated against a version of the IDL. If we upgrade our server and the clients aren't updated, they would fail. So we quite often end up in a model where we're forced into generating new interfaces to support things that we want that the clients we already had don't understand. We said we'd rather do messaging instead. So rather than asking you to basically step by step to make a cup of tea for us, we actually want you just to say, I'd like a cup of tea. When we talked about the difference between a command message, where we say, as an imperative instruction, please do this for me, and an event where I indicate my status and desire basically for tea. And then we looked at the comparison of temporal and behavioral coupling, and we said the best option for us, which has low behavioral coupling and low temporal coupling, is events, right? Event-driven systems. That if we are prepared to accept some slightly higher behavioral coupling, because I know that you are basically responding to my commands, then we can have a command-oriented version. We don't want to go for distributed n-tier systems using remote procedure calls, and that REST is okay, provided we bear in mind that we are temporally coupled. You can do a temporal coupling, by the way. The classic way the web does that is to essentially say, well, I have more than one server I can talk to. I have a pool, and I stick it behind a load balancer, and effectively the load balancer handles essentially making sure we are up. Okay, I'm right at time, and you may want lunch. So I'm happy to take questions. I'm also happy if you just come and find me at some point and ask me questions if you want to. Okay? Anyone? All right, I think we're done. Thank you.